We're going to start our discussion of differential equations with some definitions and some common terminology that we're going to use throughout the course. So, an equation containing the derivative of one or more unknown functions or dependent variables with respect to one or more independent variables is said to be a differential equation. So when we use the term differential equation, we're talking about this general setup. Now, differential equations can take the form of being an ordinary differential equation or a partial differential equation. In an ordinary differential equation, we have just normal derivatives that you've dealt with in Calc 1 and Calc 2. If we start talking about partial differential equations, we're talking about partial derivatives that you've encountered possibly in Calc 3. The purpose of this course and the focus of this course will be on ordinary differential equations. So don't worry if you've never seen a partial derivative before, so the idea of partial differential equations scares you a little bit. We'll be on the ordinary differential equation train here. So to start out, we need a little bit of notation. So depending on your experience with calculus and where you've used calculus before, you may have seen any of these four notations. The two most common in the math realm are Leibniz notation and prime notation. So you've probably seen these things where I've denoted the first derivative with the pink color and the second derivative with the purple color in each of these. Now, if you've done any physics or engineering, you may have seen dot notation, where we take our variable that we're taking the derivative of, and we put a dot over it, and however many dots are over it, that indicates what derivative we're talking about. And finally, if you have done Calc 3, seen some partial derivatives, that this subscript notation is very common. So this is telling us that we have y and we took the derivative with respect to x. The subscript is telling us what we took the derivative with respect to. So again, the first two are the most common, and those are the ones that are going to be used throughout this course. So now let's talk a little bit about the order of a differential equation. One of the skills that you'll need as we move on is to be able to determine the order of a differential equation when you look at it. So the order of the differential equation is determined by the order of the derivative. So the order of the largest derivative there. So here I have, in my pink equation, I have a second derivative, and then I have a first derivative, and I just have y, and nothing else with my dependent variable there. So that second derivative makes this a second order differential equation. Now, I can look at this purple equation. I have a first derivative raised to the fifth power. Raising it to the fifth power doesn't change what derivative it actually is that I'm working with. So in this case, even though my first derivative is raised to the fifth power, it's still just a first order differential equation. Another way you'll need to be able to differentiate between different differential equations is to notice the difference between linear and nonlinear ODEs. A linear ordinary differential equation, all of the derivatives and the dependent variable, so everywhere the dependent variable is involved, should be a linear term. If there's anything that's nonlinear about it, being exponential stuff, trig stuff, things taken to powers, anything that counts as these nonlinear equations that we have, then it is not a linear differential equation. So taking a look at my first equation here, I have a second derivative plus sine of y equals 4. Sine of y is not a linear term, so this is a nonlinear ODE. Looking at the second equation here, I have the first derivative taken to the fifth power plus y equals 0. The y is a linear term this time, but taking my first derivative to the fifth power, that's a nonlinear function, so this is a nonlinear ODE as well. Now, taking a look at my third function here, I have 3 times the fifth derivative minus the first derivative equals 2. These are all linear things to do. Taking a constant multiple is a linear function, and so this one is a linear differential equation. Now it's really important if, say, I had sine of x instead of sine of y in my first equation, that one would also be linear. So we can do whatever we want to our independent variable. It's what we do to our dependent variable and its derivatives that matters for our classification of our ODE. Now let's talk about the solution of an ODE. That's one of the purposes of this class, is to solve differential equations. So we want to be able to solve them. So let's talk about what that even means. So any function defined on an interval and possessing at least n derivatives that are continuous on the interval, which when substituted into an nth order ordinary differential equation reduces the equation to an identity, that's said to be a solution of the equation on the interval. So whenever we talk about solutions of ODEs, we need to be talking about an interval that they're a solution on. This makes them a little bit different than functions. So we might have an equation that is a function, that's a function and has some domain or whatever. And then we can also talk about that same function, that same equation, as being a solution to our ODE if it's a solution on some subinterval of its domain, which could be its entire domain, but also could be just a subinterval. That interval that we're talking about goes by a lot of different names. So you might see interval of definition, interval of existence, interval of validity, or the domain of the solution. All 4 of those are valid things to call this interval. Some other things that might come up. The trivial solution will almost definitely come up. The idea here is that if we have a solution that's the same as 0 on the entire solution interval, then it's the trivial solution. So even if it's not 0 outside of the interval, it's still the trivial solution because it is 0 within that interval. Whenever we talk about a solution curve, all we're doing is talking about graphing the solution, drawing that graph. When we talk about explicit solutions, this is like an explicit function that you saw maybe in Calc 1. They talked about explicit functions where you can write y equals f of x. And so you have your dependent variable equals some function of your independent variable, and you can actually write it that way. So that's an explicit function, and explicit solutions look like that. The other type of solution that we come across is an implicit solution of an ODE. An implicit solution, we have a relation g of xy equals 0. That's an implicit solution of an ordinary differential equation on some interval, provided that there exists at least one function that satisfies the relation, as well as the differential equation on I. So these implicit solutions, whenever we have them, you're going to have to do implicit differentiation to check to see that they are solutions to our differential equation. With explicit solutions, you'll be able to take your pick of ways to differentiate to verify those. Now, there's also different types of solutions and families of solutions that we talk about. So families of solutions, the idea here is we can have different parameters. If you remember in integral calculus, when you had an indefinite integral, you added a constant. That constant was a parameter. And that parameter could take on different values, and any value it took on, that was still a solution. So this is the case here with our differential equations. In order to solve differential equations, we're going to be taking integrals, we'll be taking indefinite integrals, and we'll end up with constants. And depending on the order of the ODE, we'll be taking different numbers of integrals, and we might end up with multiple parameters along the way. So when we talk about a one-parameter family, it has one constant, one C value that's variable, that's a parameter that can change. If we talk about an n-parameter family, there are n constants. So I can talk about a 3-parameter family, a 50-parameter family. It'd be crazy. But we can talk about any number of parameter families. Now, if there are no constants, there's 2 different categories that a solution could fall into. One is that it could be a particular solution. So that's one where I had one of these families and I chose a specific value for the constant, or I solved for it given some additional information about the ODE. That gives me a particular solution. There's no constants, but it was part of a family to begin with. Another type of solution that we might encounter is a singular solution. This one also has no constants, but it's not a part of one of these parameter families. It sits alone outside of these families. So it has to have the specific values that it takes in order for it to work. There are no parameters that we chose values for or solved for based on other information. The nature of the differential equation forced it to have that solution. And finally, the last thing that's going to come up in this class as far as terminology goes big time is a system of ordinary differential equations. So everything we talked about here is just with one differential equation, but we can actually have entire systems of differential equations. So we'll be talking about those. Solutions to these have to be a solution to all of the differential equations in the system, the same way a solution to a system of equations has to be a solution to all of the equations in the system. So, like I said, this is like all the definitions, terminology, big idea stuff of the course, but as we come along through the course, we'll be adding more stuff along the way, more detailed, nuanced stuff. But now you have an overarching idea of a lot of the words and terminology that are going to be thrown around.